Okay, this is Kinetics Part 2. One of the things we talked about in Part 1, we talked about that if you were to increase the concentration of the reactants, then usually it should speed up the reaction because there's more molecules, they would be bumping together, should make a faster reaction. Well, the thing about that is that that's not always the case. So what we're going to learn how to do is to find the rate law. And this is all about concentration. Again, concentration could be in moles, it could be in molarity, grams, etc. So some sort of amount. And changing that and seeing how it affects the rate and to what power it affects the rate. So on your sheet it talks about what is rate law, and it's just an expression. So we're going to learn how to write a rate law for a reaction, and we're going to learn how to figure out if we change the concentration, what's going to happen to the rate, with the speed of the reaction. Does it have an effect, and to what effect would it change? And so our basic equation looks like this, and it's just rate equals, K is going to be a constant, and we'll be dealing with a constant when we start doing half-life problems. And it's going to be your reactant, so I just have A and B. It could be hydrochloric acid or some sort of reactant. The key word is reactant, not product, reactant. Raised to some sort of power, and usually you have 1 to 2 reactants. Rarely do you have 3 reactants going on. And so we're going to learn to do this, and so you can write all this stuff down, but we're going to be walking through this as we walk through the video. All right, so in order to figure out the rate law, which again, in this case, we have A and B reacting together making C, so some sort of synthesis reaction, it's going to look like, and I'm at the top there, rate equals K, and your reactants, in this case being A, raised to some power, and your book uses M. So you can use M, you could use X, you could use Y, it doesn't really matter. So some unknown power there, and we have this reactant B here, and it's going to be raised to some power. So this is what we're going to be trying to figure out. We're going to be trying to figure out the power of M and the power of N, and there's a process to do that. When I first started teaching, I just showed students just to look at a data table and be able to tell, but I learned real quick that the AP, and I know we're not an AP, requires the mathematical interpretation. So we're going to make sure we can do it mathematically. So in order to do this, you're going to be looking at a data table that has several experiments in it. And so in this case that we're looking at right now, there are 3 experiments. And so if you'll notice in experiment 1, you started out with an equal amount of A and B. And this is how the rate at which C is forming, 4 molarity per second. Now that would be the same rate that A is going away and B is going away, because this is a 1-to-1 ratio. So I just used C, but again it's the same rate. So then we did the experiment again, and we did some timing. But if you'll notice, what did we do different? We have doubled the amount of B going on. And if you'll look, the rate didn't change, and that's kind of what we need to start looking at. The rate didn't change, even though I doubled the amount of one of the reactant that's in there. And then I did the experiment a third time, and this time I didn't change B, but I changed A, and I doubled the A, and the reaction, which was going at 4 molarity per second, is now going to 16. So it is now 4 times faster than it originally was going. And so that's what we're going to be looking at. So in order to do this, in order to solve for the M and the N, we're going to pick 2 experiments to work with. So you're always going to be working with 2 experiments. And in the beginning, when you know nothing and you have no variables up here, you want to pick 2 experiments in which one of these would be the same. For example, if I'm trying to solve for M up here, which has to do with concentration of A, I don't want to be really worried about B. And so if I don't really want to worry about B, I want to pick 2 experiments in which B never changed. So we didn't change B, we only changed A. So if you'll look, when I didn't change B, would it be experiment 1 and experiment 3. So B is going to be the same, but yet I've changed the A. I've doubled the A. So I'm going to use experiments 1 and 3. And I'm going to be setting these up as almost like a fraction and looking at each other. So when I set up, if you like fractions, then it doesn't matter what order you do. I'm not such a big fan of fractions, and I kind of like whole numbers. So I always look over here at the rate, and I always want to put the larger rate on top. So the larger rate here would be experiment 3. In experiment 3, it was going faster. And again, it really honestly doesn't matter as long as you don't mind dealing with fractions. So what I'm going to be doing is putting experiment number 3 over experiment number 1. Experiment number 3 over experiment number 1. And I'm going to be filling in, what's all the way at the top there, let me just rewrite it. This little expression, rate equals k, a to some power, and b to some power, because those are my reactants here. They won't always be A and B. You will actually put the real chemical symbol when you have real compounds in there. So I'm just going to fill this in, and I'm going to do this for experiment 3. So the rate is here, and it was 16. So 16 molarity per second equals, K is a constant. Nowhere in here does it have K. So I'm just going to write K. And this is letter A, the concentration of letter A. In experiment 3, it was 0.2. I'm not going to put the 0.00. I will put my unit there. Okay, and that's raised to some power, m power. And then my B, I left that at 0.1. I will put my unit, and it is raised to the n power. So all I did was put the numbers in for that. I don't know K, so I can't put in K. Alright, so now I'm going to do this for experiment 1. And so for experiment 1, my rate is 4 molarity per second, 4.00. And then K, we still don't know. And then my A was 0.1 raised to some power. And then my B was 0.1 raised to the same power. Alright, so the reason we picked the experiment 3 and 1 is, do you notice it's 0.1 to the n divided by 0.1 to the n? These are the same things, so they cancel out. So that's exactly why we picked them. So we wanted to concentrate on A, so we didn't really want to look at B. So do you see it's a K on top and a K on bottom? Those constants are the same, so they're going to cancel out. And my units cancel out. We've got a lot of canceling going on. My numbers don't cancel. Your exponents don't cancel out, unfortunately. So now you have 16 divided by 4, which would equal 4. And then you've got 0.2 raised to some power divided by 0.1 raised to the same power, and that is important. It's raised to the same power. And so if you do that in your calculator, which hopefully you don't need to, that would be 2 raised to the power. And hopefully you don't need a calculator for this as well, because to figure out what power, it would be the second. We call this a second order reaction. Okay, so this is called a second order reaction. If you get weird numbers, or if you had done like fractions and stuff like that, the way you solve for this power, if you should have learned that in one of your math classes. If you didn't know, or you just, clueless, the way you do this is you take the log of the side that doesn't have your exponent divided by the log of the one with your exponent. So in this case, it would be log of 4 divided by log of 2. If you do that in a calculator, you get 2. Of course, this was a very easy one, so I'm just saying as they get harder, when you lab, you're going to get some not so nice numbers, and so that's how you would solve for that. Okay, so we have now found, let me get my little eraser, we have now found that A is raised to the second power. So we did all that work to get that little number there. Now, once you have one of the numbers, you could actually solve for the other number quite easily, but I'm using any two experiments and doing the same process, because once you have one of the numbers, it's just a plug and solve. But once you have, again, you don't need it where they cancel out. But if you want to make it easier on yourself, if I want to figure out what B is and to make it easy on myself, I could simply now, I'm going to erase because this thing won't scroll up. I'm going to pick 2 experiments where A will cancel out. I don't have to deal with A, meaning I never changed A. So if I look at that, that would be experiments 1 and 2. So I want to do experiments 1 and 2. So I decide which one goes on top, which one goes on bottom by the rate, the larger rate. Well, these rates are the same, so it doesn't matter. So I'm going to put experiment 2 over experiment 1. It doesn't really matter, so you could do it either way. So my rate is 4 molarity per second. I don't know why I have that decimal there. Equals, K, again, I don't know. I know it's going to cancel out, but yes, you must put it, okay, because it is part of the rate, and if you don't get in the habit of putting it, you won't put it later when you really do need it. So then we're going to just plug in. I'm doing experiment 2. So A was 0.1. There's my unit. I actually know it was the second power, so I can put that in there. And then we're still doing experiment 2, so our B was 0.2, and it was raised to, I don't know, it was raised to the n power. And this is divide by, and so then it's 4 molarity per second. Okay, my A didn't change. And then you've got 0.1 raised to the n power. So hopefully you'll see those will cancel. 4 divided by 4 is 1. Your K's will cancel. Your molarities will cancel. Actually, your 0.1s will cancel. They'll all go away on us. And now we got 0.2 raised to the n power and 0.1. This is 2 raised to the n power. Now you should have learned in your math class, anytime something's to a power and it equals 1, it always equals 0. We call this a zero order. Zero order means it has no effect on the experiment whatsoever. And we saw that. We saw that doubling that B did not change the rate. And that's what a zero order does, meaning it has no effect whatsoever. So I could have put 100 times more of B in there, and that rate's still going to go for molarities per second. So some of you are saying to yourself, well, I could just see it. Can I just put 0? And the answer is no. You must mathematically prove it. So there is this math portion. It's kind of like your math teachers. Show your work, show your work, show your work. Okay, so we have now found that to be to the 0 power. So there's the way my rate law would look. So this is actually the rate expression. This is your answer here for letter A. Now honestly, if it's to the 0 power, you don't need to write it at all. You could just take it out and it would look just like that. Because if it's to the 0 power, it's just 1. It's not really needing to change. So this is called our rate law. And so to figure out the next question, what determine the overall? Well, we said that m plus n, whoops, that's not an n, getting ahead of myself there, n equals the overall. So we had this as 2 and this as 0, so our overall order is what we call a second order reaction. Now this will start making more sense the more we get into this, but right now it's probably going to be quite fuzzy. And you don't have to show your work for adding the two numbers together. I'm just emphasizing it on the PowerPoint. All right, our next one says, calculate the rate constant with units. Well, the rate constant is that letter K. So in order to find the rate constant, you pick any experiment. I'm just going to suggest that you always pick the first experiment. It honestly doesn't matter because you should get the same answers with every experiment, but we're just for simplicity, we'll just pick experiment number 1. So we're going to take these values and we're going to plug them into our rate law. Well, our rate law, let me go to a blank page here so we can see. So our rate law looked like this for this equation, and it was a squared. I don't need b in there because b was not changing, so I can get rid of him because it's just going to be the 0 order. So I'm just going to take experiment 1, and hopefully you're looking on your page, or you can back this up. We're looking at the PowerPoint, but it is on your note page. So our rate was 4 molarity per second. The K is what I don't know. And then we plug in A. We don't need to plug in B because it is to the first order. All right, so now all we got to do is mathematically solve for K. So basically we're going to divide both sides by 0.1 molarity squared. You've got to make sure you square that 1. Okay, so zero point 0.1 squared molarity squared, because that's what's happening. So most of you can get the math number, and the mathematical number for this one is 400. And I don't know what the sig digs was. We used 3 in the problem. Yay. So 400, we can make 400 have 3 by putting a nice little decimal there. So now let's talk units. Now if you'll notice, these units here are going to cancel. You've got 1 molarity on top and 2 on bottom. Hopefully you realize that one of these will cancel out and leave you with just 1 on bottom. Well, the fact that it's on bottom, and hopefully you remember from last time, it can be written as that, the fact that it's on bottom. Well, the seconds, because it's a per second, it technically is on bottom as well. So maybe you've dealt with that in math where you have a fraction over, and so that seconds is also over 1. So this is the way that unit is going to be written, and that is the way we're going to write that unit. So this is your K's unit. The value is 400, but its unit is molarity to the -1, seconds to the -1. I just want to start out point out that the overall order was 2, and this is a -1 and a -1. If we add them together, we get a -2, but the absolute value of that would be 2. We're going to start to see a pattern with K's units. Okay, so that is so we could even, if we wanted to write the right law, we could even rewrite it and put K in there in all its glory with its units, etc., and it would look like that. That would be our rate law. All right. So moving on, basically we have the same type problem, but this time we've got moles and we've got seconds instead of molarity per second. We've got moles per second, and we actually have some real chemicals in here instead of just A and B. So we have nitrogen monoxide plus hydrogen making dihydrogen monoxide and dihydrogen monoxide and dinitrogen monoxide, or water for one of them. Okay, so if we look at this, our general formula is going to look like this. Rate equals K, and it's going to be your reactant, which is NO, raised to some power that I don't know, and then it's H2 raised to some power. Okay, so we're going to start, and we're going to try to solve for M first. In order to solve for M, we would like 2 experiments because we don't have either one of these variables. You would like to pick 2 experiments where H2 is going to cancel out. I will tell you, if you have 3 reactants, then you want to pick 2 experiments where the other 2 of the 3 reactants will cancel out. And on the homework page, there is a couple that have 3 reactants. So it works the same way. You would just have 2 canceling out instead of 1 canceling out. So it's not any harder, just get a little longer. All right, so hopefully you recognize that 1 and 2 are the ones that we want to choose. We want to come over here and pick the one with the larger rate. You have to be careful with this because you would think 2.5 is larger than 1, but honestly this is to the -4th power. This is actually a larger number than the 2.5 to the -5th. So we're starting to deal with scientific notation there. So in order to figure out the M, I would choose experiment, and again you can do it backwards, you'll just get fractions, and I just don't like fractions. Experiment 2 over experiment number 1, and so then we would put in the rate, and I'm just going to leave out the significant digits. It is moles per second. You don't have to have the right significant digits in your work, but you do need to have your units. Equals K, and then it would be the NO's value, which is 6.4 times 10 to the -3rd moles raised to some power times, if you do have 3 variables, I would not suggest you use M and O because you think the O is a 0 sometimes. Just FYI on that one. To the N power. All right. Oh, I didn't catch myself there. That should be 1.28. So sorry. When you're taping live, it just sometimes doesn't work, but that's okay. There we go. Now we've got that correct. Did I get that one correct? Okay. And so now we'll have 2.5 times 10 to the negative fifth. Okay. And then we will have what I accidentally wrote before. And then this is the same because we want it to cancel out. Many times students will say, I know it's going to cancel out, I shouldn't even have to write it. And the answer is you must write it and you must show it canceling out. So not necessarily showing canceling out. And the K's are going to cancel, and of course all your units are going to cancel. And so we're going to be left with these pretty numbers that we can calculate out. And so if I were to calculate those out, hopefully you would see that that's going to become 4. And if you will divide that out, you would see that it is 2 raised to m power. And so we've seen that one before. So our m is going to be second order. So we now know that this is to the second order. So once you've got that, again, you don't have to pick two experiments where the other two cancel out, but it just makes it easier if they will cancel out. So there's one on the worksheet that you'll find one, and then you're just going to have to plug in and solve to solve the other one. You won't pick two experiments that they'll cancel. You'll pick two experiments and just solve mathematically. All right, so now I want to solve for H2. So I want to pick these two experiments so that those will cancel out. And I want to put the bigger one on top, so that is going to be experiment 3 over experiment 1. And so I'll have 5 times 10 to the negative fifth. I'm just going to go ahead and write this other guy's rate while I'm here. And then that's going to equal, and so now back on this line, we're going to have K, and we're going to have 6.4 times 10 to the negative third. And I know it's to the second power. And then 4.5 times 10 to the negative third. And it's 2, I don't know, over K. I lost this one. 2.25. Alright, so if I cancel out, again, if this were not the same number, it would be okay because we could mathematically solve this value. So just let you know that. Okay. So now when I divide these out, you'll get 2 on this side. When you divide this out, you get 2 raised to the n power. Well, hopefully you know that n is 1. And so our rate law would be rate equals, and you're welcome just to put K, but we're not going to put A and B. We're actually going to put the real chemicals NO and H2. So we're going to put, so it's nitrogen monoxide, and it was raised to the second power, and then it is hydrogen, and it's raised to the first power. Now you don't actually have to write the 1 because 1 would be understood, but sometimes students will forget things, so maybe you want to write the 1. And so what would the overall order be? The overall order, that's a really hard question. The overall order is 2 plus 1, so that it gets us an overall order of 3. That overall order will mean something to us when we start doing half-life problems. And then to solve for K, we pick any experiment. Again, I suggest experiment number 1. You're going to just plug into that expression, and you're going to solve for your K. And so I've got that one going on a blank page here. So we've got rate equals K, and it was NO to the second and H2 to the first. And so if we pick that first one, moles per second, equals K, and then we've got the moles of this. I've switched pages, so you've got 6.4 times 10 to the negative third squared times 2.25 times 10 to the negative third. I lost my units there. There's a mole. There's a mole. Alright, so you could do the math if we move this number over squared, move that number. So let's talk about the number value you get. You should get a number value of 271. Okay, so that's the magnitude, but we want to talk units. So I'm just going to look at units here. This is a molarity squared. I'm sorry, a mole squared. And this is a mole, so you got mole squared times mole. So can you see that that would be a mole cubed? So we're going to end up dividing by mole cubed, which will cancel those moles out. Again, I'm just working with the units. Hopefully you can get the number. So I've got a mole cubed. So I've got 1 mole on top and 3 moles on bottom. So that's going to cancel and leave me 2 on bottom. So this is actually going to be a mole to the negative 2, and it's going to be a seconds to the negative 1. Do you remember what that overall order was? That overall order was 3. Here's 2 and 1. 2 plus 1 equals 3. There is a definite pattern to the overall order in K. So this is just a pattern you'll start to see. Overall order and units on K. So we'll talk about zero order well, in a zero order, it's just going to be rate equals K. So whatever unit your rate is, that's the unit of your K. So it's going to be some sort of amount, and it's going to be per some sort of time unit, such as molarity per second, grams per year. So zero order is going to be the same as the rate. So first order is always going to be some sort of time raised to the negative 1 power. Days to the negative 1, seconds to the negative 1, years to the negative 1. A second order is going to be some sort of amount unit, molarity, moles, grams, to the negative 1, and a time unit to the negative 1. If it's a third order, it's going to be an amount to the negative 2 and a time to the negative 1. Can you see that time always stays negative 1? So maybe you could predict this one. If it's a 4, which is rare by the way, you get negative 3 here and a time amount to the negative 1. Hopefully 1 plus 1 is 2, 2 plus 1 is 3, 3 plus, and time is always staying a negative 1. Zero order is the only one. And very rarely would you ever see this, but I think there's one like this on the worksheet. If you had a fifth order, you would get an amount to the negative 4 and a time to the negative 1. Definite pattern going. So when I mean amounts, again, that is like moles or molarity or grams. So you can see, and time is going to be seconds, years, days. It's going to be some sort of time amount. So that's what we're going to see for the units. And if you go back and look at the two examples that we did, you'll see that holds true. Okay, so what in the heck does all this mean? Well, what all this means, these order numbers, the little values that we're putting up here, okay, it tells us how, if we change this guy's amount, to what extent will the rate change. There is a K in there, but K is a constant, so constant's not going to change. So we're just going to look, and we did this through the notes on your note page. You can fill it in and pause me, and then I'll talk, whichever you want to do. But these are the individual orders. We're not talking about overall orders. We're talking about the individual numbers that we're putting. That's called the order number. So if something's a zero order, well, anything raised to the zero order is 1. So if your rate were to the 0 order, because the K is always in there, if I were to double the amount inside, so instead of A, I've got 2A, if I raise that to the 0 power, well, that's not going to change anything because this would be rate equals K and this would be times 1. So then nothing's going to change. So if it was going 20 moles per second, it's still going 20 moles per second. So it's not going to change whatsoever. If it's a first order, so raised to the first power, if I were to double, so instead of A, I have 2A. So what I'm doing to the concentration is going inside. This is the order number. It goes out here. So what would happen to the rate? Well, it would be 2 raised to the first power. 2 raised to the first power is 2, meaning the rate's going to be twice the amount it originally was. So if it was going 40, if it was going 20, it's now going 40. If it was going 40, it's now going 80. It's doubling. So I double that concentration, it's going twice as fast. If it's a second order, basically we're going, we double the amount, and it's second order, it's going to be 2 squared the rate's going to change by. So it's going to be 4 times. Oopsies. Should have put a 2 there. What should I have put there? I should have put a 3. The order number goes out here. And what I'm doing to the experiment goes in here. So I'm doubling it. So I'm just putting A for amount. So doubling the amount, doubling the amount. So what's going to happen? Well, if it's 2 to the third is 2 times 2 times 2, it's going to be 8 times faster than it was. So it was going 20, it's now going 160. And then if it's to the fourth order, it would actually be 16 times faster. So that's what all this stuff means. So if we look at tripling, tripling means I'm going to put a 3 in there. Well, if it's to the 0 order, no change. And if I triple and it's first order, it's going to triple. And if I triple and it's second order, it's 3 squared. 3 times 3 is 9. Hopefully you're seeing this pattern. That should be a 3 because I'm doing third order. So 3 times 3 times 3 is 27. And if it's to the fourth order, 3 times 3 times 3 times 3 is 81. So that's what the order tells us. So for example, well, there's your assignment to finish up the worksheet, and the answers are on Edmodo. I just wanted to show you one thing. If something were first order, okay, first order, and we made it 100 times more concentrated, okay, the rate is going to be 100 times faster. So that's what it's going to mean. So this inside is your change, not your charge, but your change, and this is your order number. So hopefully that helped. Please send me a message on Edmodo if you need help. So have a good evening.